So the curved lines are sort of what you'd get from a continuous model. So the depth of the aerobic layer is H1. And imagine that the ammonia flux looks the same way. There's no change in the anaerobic layer, and this thing's a straight line connecting the two endpoints at the top and at the bottom. So let's calculate the ammonia flux from the way you do it if you were doing it from the pore water. So you'd have the diffusion coefficient times the derivative, which you're going to approximate as a straight line, which is the difference divided by the depth. So I'm approximating the gradient by this gradient, which then I can define the surface mass transfer coefficient as the ratio of the diffusion coefficient divided by the aerobic layer depth. So far I'm just defining things, I haven't done anything clever yet. Clear? Now you can make a similar argument for sediment oxygen demand. The sediment oxygen demand is the diffusivity of oxygen times the oxygen gradient at the surface, which is equal to the difference if you assume it's a straight line, which you then divide by the depth. And the oxygen concentration at the bottom of the aerobic layer is 0. That defines the bottom of the aerobic layer. And so finally, the SOD, the sediment oxygen demand, is the surface mass transfer coefficient for oxygen divided by the overlying water oxygen concentration. And therefore, if you define the surface mass transfer coefficient as this ratio, which is that, you can get the surface mass transfer coefficient is the sediment oxygen demand divided by the overlying water oxygen concentration. And that was the key to understanding how to analyze data, because now those are measured. So if I have a measurement of SOD and I have a measurement of ammonia, I got half of the problem. Right? I now have, and if I assume the diffusivity of oxygen is equal to the diffusivity of ammonia, which is such a small correction that it gets lost in the noise, so we just assume it's the same. Now I have this number. And so then what I need is that number, and then I can predict ammonia. Clear? So how do I get H1? Remember, I needed H1. I got the surface mass transfer coefficient, but I haven't gotten H1 yet. Got that guy. Need that guy. And then all I'm left with is the decay coefficient, and that I can fit to the data. So how do I get H1? Well, H1 is equal to the, remember the SOD over O2 is the diffusivity over that, so if you flip it over you get that. And we're defining the ratio of, it's such an important quantity that we define it as S. So every time you see a little s, it's SOD over overlying water oxygen. Okay? So I've got H1 is equal to that. Well, what I really need is the reaction rate times H1. And that's equal to that. So if I so I need this. S gets rid of the H1. And so the diffusivity of oxygen, if I divide by H1, that cancels out the S and leaves only the diffusivity and the reaction rate. And I regretted doing this many times, but I defined what was called the reaction velocity because it has units of meters per day. And it's really the square root of the diffusivity of oxygen times the first order reaction rate. It's just a trick. And I did it because it makes the units. So then if you do the substitutions, you end up with, this is observed, SOD over DO. And this is the parameter that you don't know. And so the ammonia flux is related to the diagenesis flux times the ratio of S squared over S squared plus kappa squared. That's what the algebra is telling you. So if I lost you at this turn, S is SOD divided by, if I bring H under there, No, I want this. I don't know this and I don't know that, but I can get this because of if I just make that definition, then I know everything. It just comes out in terms of S and kappa. There's no H1 in here anymore. So H1 basically comes out of SOD over oxygen if you know the diffusivity. Think of it that way. If I know that number and I know that number, I got that number. That's basically what's going on. Clear? So now I've got a model I can test. I can take ammonia fluxes, or I can take ammonia fluxes over ammonia diagenesis, and it should plot like that. And this is the curve of all of the ammonia flux data versus SOD over overlying water oxygen data that we had in the Chesapeake Bay data set. At this point, I would like to say that we could have never built the sediment flux model without the work of Mike Kemp and Walt Boynton and Jeff Cornwell and all the people at both CBL and at the SEAS, the University of Maryland Ecological Center. I mean, they spent 2 years getting the data to look properly. We threw out the first 2 years of data because their measurement techniques weren't reproducible. They couldn't keep getting. So you have to have a good data set. If you haven't got a good data set, you got a real problem. It's still pretty scattered. It doesn't look terrific, and there are log scales. But if you average them up in bins of 10th log units in S, you get that, which is a remarkable fit. By the way, notice that I haven't normalized out ammonia flux. This thing is what I should have here is that. And we're just ignoring it. We're assuming that that's an average over all of the data. So the scatter is some average. So the number that ends up, if you look at that's the sort of global average of ammonia flux, which is like 100 milligrams per meter squared per day. Typical ammonia diagenesis, nitrogen diagenesis. So far, so clear? So, key, 1, you can get the depth of the aerobic layer if you know what the SOD is. Because you need the SOD and you get the overlying water from the water column model. So if you know what SOD is and you know what the overlying water is, you got the surface mass transfer coefficient and you have the depth of the aerobic layer because you know the diffusion coefficient of oxygen. Clear? That's the key. Once you have the depth of the aerobic layer, then you're set because you got the depth of the anaerobic layer, you got the depth of the aerobic layer. The aerobic layer keeps varying depending on what the SOD is. Of course, I need the SOD. We'll get to that. But if I could compute the SOD, then I have the depth of the aerobic layer. Okay? Questions? Comments?
Tom?
Yeah.
Could you go back to
Sure.
one slide? Yeah, so could you explain a bit more on define reaction velocity?
Yeah. If you think about, so what do I need? I need the first order reaction rate, and I need the depth of the aerobic layer, right? The first order, the mass transfer coefficient, meters per day, is the SOD divided by the overlying water oxygen. That's clear, right? I need H1. If I know S, and I know that, then I could calculate H1 directly. But it turns out if I bury that with the reaction rate and make that a new unknown constant, that's what kappa is. All right, so what I'm doing is just burying the diffusivity of oxygen inside the reaction rate and making that product the new unknown. It's just convenience, so I don't have, DO2 sitting around in all of these equations. That's all it is. There's nothing complicated or fancy. It's just, if you follow this, right, this has got to be the depth of the aerobic layer, and therefore, it's that. Okay? Yeah?
Yeah, I think kind of earlier we said that the aerobic layer thickness was 10.
Yes, but it varies.
Okay.
It varies a lot.
Okay, that's my question.
It varies a lot because SOD is varying.
Yeah, That's it.
right? And or the surface mass transfer, but primarily because SOD is varying. As you can see, if the SOD is very large, this thing's very small, right? And that's important because all the aerobic reactions are happening in the aerobic layer. So if the aerobic layer gets very small, you don't get any nitrification. Whereas if it starts getting very large, you get a lot of nitrification.
Yeah, if you go back to your original equation, you were doing the comparison. Yes, which one? Let's see. Right, yeah, I guess the JNH4, so you were mentioning
ammonia
that
flux.
KL, the mass transfer coefficient is very large, everything comes back, but if the reaction rate times the depth, but if the depth is getting smaller, then that drives your KL001 becomes the important and everything's coming back.
Exactly.
But if the H1 is really thick, then you get a lot of nitrification occurring and your flux is reduced.
Precisely. Got it?
Total thickness of the sediment layer is still 10 centimeters.
10 centimeters, right. So you're subtracting millimeters off of 10 centimeters. In very aerobic systems, we sometimes get a centimeter for the aerobic layer depth. For sandy sediments, not very much. So far, so clear? Nitrate. Well, nitrification can only occur in the aerobic layer, so we've got ammonia going to nitrate by the same reaction rate as in the ammonia flux model. But we also have denitrification in the aerobic layer going from NO3 to N2. And you might ask yourself, why have we got nitrification in the aerobic layer? It's supposed to be an anaerobic process. Kemp and company had a PhD student that showed that there were microzones, is how they interpreted it, where denitrification was actually occurring in the aerobic layer in little zones of anaerobic. In the reanalysis of the sediment flux model that happened a few years back when Jeremy Testa and Damian Brady wanted to do a project, and I said to them, and Walt Boynton had put together the whole universe of Chesapeake Bay data. I said to them, take the sediment flux model, please, and show where it's broken. I don't want you to tell me where it's right. I want you to tell me where it's wrong. And Testa figured out what was going on here. I couldn't make the model work without having that in there. It simply wouldn't reproduce what we saw. And it turns out that Jeremy had the right answer. I won't tell you about it because it's a bit complicated, but if you read the papers, which are loaded up on the website, you can find out how that was fixed. But the current state of knowledge when we built it was that this was occurring in microzones. There was no nitrification in the anaerobic layer, there was simply denitrification, and the end product was in both cases nitrogen gas. Okay?
You just let's say in the Chesapeake Bay, which one is dominating?
You'll see. So the mass balance equations are all the same, right? You have reaction rate, you've got surface mass transfer to the anaerobic layer, and then the source from ammonia oxidation. And in the anaerobic layer, you simply have denitrification and the transfer up. So you can solve for the nitrate in the aerobic layer, and you get the source, you get the transfer from the overlying water. So this is the sources coming in, and these are all the loss terms. Denitrification, surface mass transfer out, and then a reciprocal of the sum of the reciprocals. You can play with the algebra, it's simple algebra, and you can convince yourself what's going on. Also notice that the nitrate concentration in layer 2 is determined by the rate at which it's being denitrified relative to the rate at which it's being transferred down. Same kind of thing. Define reaction velocities in the aerobic layer. To keep things looking the same, I define the anaerobic layer reaction velocity as the first order rate constant times the depth of the anaerobic layer, just to keep the units right, and then some algebraic simplifications, and you end up with this. The concentrations aren't all that important. What's important is the flux. So what's the source of nitrate due to nitrification? Well, it's the diagenesis rate, plus what's coming down from the overlying water, plus what's being transferred to what's being transferred up by the surface mass transfer coefficient. You go through the algebra. And it turns out it's just what isn't escaping as ammonia must be ending up as nitrate. It's the only two places it can go. The reason I'm taking you through this is easy, right? So if the model isn't doing things like this, you know that there's something wrong. I spent most of my time in my professional life trying to figure out why the computer programs were giving us wrong answers. That's all. When things were working right, the young engineers never came knocking on my door. So senior people have to have an intuitive understanding of what the heck the damn thing is doing. And if it's not doing what you intuitively think it should be doing, then you know there's something wrong. I mean, look at the code that you're going to be going through for 2.5 days. I'll wager you there's still errors in that code. The trick is to just find this stuff. Remember when we found the mistake in an oxygen code that we had used for 20 years? So, right. So if you look at the nitrate flux, it's got two parts. The nitrate flux is the amount of nitrate that is being transferred into the system from the overlying water. There's the minus sign. Plus the nitrate that's coming out due to the fact that it doesn't end up as an ammonia flux coming out. And you can see, once again, you get these over S's and S's and so on. I won't take you through this. The time is going quicker than I expected it would. So these are the equations. Okay. So that's nitrate. So the nitrate model basically has just two things: reactions and mass transfer. The next problem is phosphorus and oxygen. Let's think about phosphorus first. Phosphate is not, it doesn't just stay dissolved in sediments. It can sorb very strongly to the sediment particles, and in particular the iron that's in sediments. This is well known to the geochemists. There are lots of models about iron sorption to various phosphate sorption to various iron. There's a famous book, Surface Complexation Modeling, by David Zombach and Francois Morel, that lays out the models at about the middle of 2000, maybe, in that time frame, maybe a little earlier. And the first thing you need to do is you need to partition it between the concentration that's dissolved and the concentration that's particulate. So here's how you do it. I give you a liter of water, sediment, okay? I take a chunk of sediment. In a liter of that bulk, there's a certain amount of dissolved phosphorus, let's say, in milligrams dissolved phosphorus, and there's a certain amount of particulate phosphorus, again, milligrams of phosphorus per liter. And if I add the dissolved plus the particulate, I get the total phosphorus in the liter. So C sub P is a bulk measurement. M is the concentration of particles in the liter. And that's got units, kilograms of, I just use suspended solids per liter, okay? So imagine I have a chunk of sediment, a certain amount is dissolved, a certain amount of particulate, and a certain amount is particles. If I define the particulate concentration as the ratio of the bulk concentration to the particle concentration, then I get the milligrams of phosphorus per kilograms of solids.